Hello, everyone. My name is Mayur Kure. Me, along with my two fellow teammates, Emmanuel and Jinwan, have worked on uh, this project where we are trying to analyze the insurance cost across the medical sector. Uh, our goal was to uncover the patterns that explain why some people are charged more than others. Over the next few minutes, I'll walk you through some of our key findings, starting with what factors are involved in calculating insurance cost, followed by exploratory data analysis, and finally some key takeaways. So let's begin by asking a simple question: how insurance cost is calculated? We all know that healthcare in the United States is very expensive. In this project, we are exploring some of the demographic and lifestyle factors like age, body mass index, smoking habits, number of children, and regional distribution. In the data set, we have around 1,300 individuals, which are spread across multiple regions. As part of the exploratory data analysis, we looked at the overall patterns. We created a number of visualizations to understand the relationship between different factors. In the first histogram, we can see that most people pay moderate charges. There are a few very high cost outliers. Smokers show far higher charges compared to non-smokers. The median price is more than double. Finally, charge rises with BMI, especially among smokers. So lifestyle choices do have a strong financial impact. When we looked at grouped comparisons, the story becomes even clearer. Obese smokers have the highest average cost, showing how lifestyle factors actually impact here. Uh, among smokers, the cost rises sharply in older age bands. Age has a upward relationship with charges, so the older you are, the higher the insurance cost. To wrap up, our ED analysis clearly shows that lifestyle and health behaviors are the strongest determinants of insurance cost. Smoking and obesity drive medical expenses significantly higher, while non-smokers and individuals with a healthy BMI tend to have much lower cost. Age further amplifies these effects. Older individuals, especially smokers, face the steepest increases. Uh, Regional distribution did not play a very important role, as well as the number of children. The cost was fairly evenly distributed across these two different factors. This concludes my presentation. Now, Jinwan is going to explore data cleaning and feature selection. Thank you for listening.
Hi, this is Jin Yuan. I was responsible for the data cleaning and feature selection in our final projects. Our datasets came from Kaggle and include 1,338 samples. Even though it looks green at the first glance, but we still perform validation to check to make sure that there were no missing value and no data times errors. In the end, we found one duplicate record and removed it because sometimes the duplicate can bias the model or lead to the overfitting, especially when the dataset is small. And we applied one hot encoding to convert category code features like smoker, sex, and region into a numerical format so the machine learning can interpret them correctly. And after that, we standardize the numerical features such as age, BMI, and children to ensure that all variables were on the same scale and contribute equally during the training. And as the usual, we split the dataset into 80% of training and 20% for testing to make sure our evaluation was unbiased and reflect the model real performance. For the feature selection, we combine correlation analysis and one-way ANOVA to identify the most meaningful predictors. Correlations show how strong each value moves with the insurance course, while ANOVA tests whether those differences are statistically significant. From the correlation result, we can see that the smoker had the highest correlation with insulin course at 0.79, followed by age and BMI. Other variables like children region sex show much weaker relationships. However, when we ran ANOVA to confirm this, we found the sex and children had a p-value below 0.05, meaning we could reject the null hypothesis. They still have a mild but statistically significant effect. On the other hand, region still showed no statistical effect on the chart, so we decided to exclude it from our model training.
Hello everyone, my name is Emmanuel Sadek. I will be discussing the model training and analysis portion of our project. Now that we have explored the data, let's look into how we built models to predict insurance costs accurately. We focused our efforts on 4 key machine learning techniques, each trained rigorously to handle the complexities of real-world pricing, like balancing risk and fairness. Our goal is to empower better decisions with easy access to data. This sets the stage for smarter, more precise predictions. Shown here are the 4 models we tested, each bringing a unique strength to the table. First, linear regression. It's the straightforward one that fits simple trends like a straight line through your data points. Next, decision tree, which branches out decisions like a flowchart to capture if-then rules. Then, k-nearest neighbors, or KNN, that looks at similar neighbors in the data to make predictions. And finally, support vector regression, or SVR, which draws flexible boundaries around complex patterns. We chose these to cover a range from basic to advanced, ensuring we find the best fit for our insurance nuances. To make our models reliable, we used a solid training setup. On the left, we have an image that depicts tenfold cross-validation. It splits the data into 10 parts, trains on 9, tests on 1, and repeats, averaging results for robust, unbiased performance. On the right, you can view the grid search results we calculated for our decision tree model. Grid search exhaustively tunes hyperparameters, akin to dialing in the perfect settings, and picks the winner based on the cross-validation scores. This combo ensures our models aren't just good on paper, they perform consistently in the real world against unseen data. Let's examine how our models stacked up. Across these charts, you will see predicted versus actual charges. The closer to the red line, the better. Decision tree shines here, with a root mean squared error of just 3,846 and an R squared of 0.89, meaning it explains 89% of cost variations. SVR follows closely at 4,063 root mean squared error and a 0.87 R squared. Linear regression hits 8,943 root mean squared error, while KNN is at 7,036. The residual plots below show errors are mostly centered near zero, confirming tight predictions. There are no wild outliers dragging us down. Based on this, decision tree is our top pick, leading with low error and high explanatory power. SVR is a strong second. It is important to note that these two excel at non-linear jumps, like sudden cost spikes for smokers, outperforming simpler models like k-nearest neighbors or linear regression. For business, this means over 80% accuracy unlocks personalized pricing, potentially cutting risks by 20 to 30% through smarter targeting. In wrapping up, our big recommendation is to go data-driven for pricing. It's smarter for business and results in happier customers. Adoption of the decision tree for capturing 89% of cost drivers like age and smoker status for accurate fair premiums, and use these models to flag high-risk profiles early, reducing claims by 20 to 30% via proactive outreach. This isn't just analysis, it's an actionable strategy to boost profitability and trust. Thank you.